we now discuss the questions that have appeared on rings from the section algebra in TS set examinations. And this discussion is relevant to JL, DL, AP set, IIT JAM, GATE and CSIR NET aspirants also. I thank my student CVR from CVR College, Sripad Venkatesh, for some of his inputs in improvising certain results. Right, let's now get into the very first question that has appeared in TS set 2023 October examination. The question number is 79 and it bears the question ID, this one. And to solve this problem, you don't need any deep results of ring theory, but if you have the general knowledge of rings, that is sufficient. Which of the following pairs of polynomials in Z5x have the same roots in Z5? So it is a polynomial ring. Z5x is a polynomial ring, and you are given a pair of polynomials in this, and you have to show that pair which have the same roots in Z5. What are the pairs? The pairs are here. Fx, first option, fx is equal to 3x to the power of 5 minus 4x square, and gf, the second one, g of x is equal to x square plus 3x. Right. Let's now consider the options one after the other. So, solution. We have a finite field Z5. Zp is a finite field when p is a prime number. Z5 and the addition modulo 5, multiplication modulo 5, Z5 forms a field. It is a finite field where Z5 is the set consisting of 0, 1, 2, 3, 4. These are the residual classes. Modulo 5. Right. Now, let's get into option 1. We have two polynomials, fx, 3x to the power of 5 minus 4x square, g of x is equal to x square plus 3x. Right. The first one is, let us consider the second function, g of x, and x is common. So, we write it as x into x plus 3 is equal to 0, and the roots are x is equal to 0, and x plus 3 is equal to 0 will give you x is equal to minus 3, where minus 3 modulo 5 is 2. Therefore, x is equal to 0, comma 2 are the roots of g of x. Now, let us test these are, is 0 a root of f of x, is 0 a root of, is 2 a root of f of x. Obviously, 0 is the root of f of x because every term consists of x only. So, let us test for f of 2. So, now note that f of 0 is 0, no problem. F of 2 is equal to, from 3x to the power of 5 minus 4x square, we have taken x square common. So, x square into 3x cube minus 4. So, put x is equal to 2. That will be 2 square into 3 into 2 cube minus 4. Now, when simplified, it will be 4 into 20, that is 80. Modulo 5 is 0. So, that means 0 is a root and 2 is also a root for the function f of x. So, x is equal to 0, comma 2 are the roots of f of x in Z5. Agreed. So, thus f of x and g of x have the same roots, namely 0, comma 2 in Z5. So, therefore, your answer to this question is option 1. And the very first option you are getting, therefore, you are getting the answer. Now, let us now try for options 2, 3 and 4 in the next slide, and we will show no to the fx and gx are not having the same roots. I will show you. So, let us get into the second slide. Right, that is the question. Those are the options. Let us take the second option. And we have already seen our answer is option 1. Right. Take the option 2. F of x is equal to x to the power of 5 minus 4x square. X to the power of 5 minus 4x square. G of x is equal to x square plus 2x. So the easiest one in this is g of x. So g of x. Now in this, x into x plus 2. These are the roots. The roots are, the factors are x into x plus 2. X is equal to 0 and x plus 2 is equal to 0 will imply x is equal to minus 2. Minus 2 is 3. Therefore, x is equal to 0, comma 3 is a root of g of x. Now, if you substitute x is equal to 0, f of 0 is 0. But if you substitute x is equal to 3, f of 3 is equal to 3 square into 3 cube minus 4. That means you have taken x cube common. So, and when multiplied and simplified, it will be 4 into 3. 4 3s are 12. 12 modulo 5 is 2, which is not equal to 0. So, therefore, this implies x is equal to 3 is not a root of f of x in Z5. But whereas x is equal to 3 is a root of g of x. Therefore, these two, f of x and g of x, they are not having the same roots in Z5. Agreed. So, the option 2 is ruled out. Option 3, you take f of x is equal to x to the power of 4 minus 4x, g of x is equal to x cube plus x. And when you factorize, it is x into x. This will imply x is equal to 0 and 4 are the roots. So, if you substitute x is equal to 0, substitute, right? And this will be 4 cube. 4 cube is 64. 4 cube is 64 plus 4 plus 4, 68. But 4 is not a root of f of x. Right. So, you substitute 4 cube 64 plus 4 68 modulo 5 is 3, which is not 0. So, therefore, 0 comma 4 is a root of g of x, but 4 is not a root of f of x. Please check. And even in this case also, for the case of g of x, if substitute x is equal to 1, 1 plus 3 plus 1, 5. 5 modulo 5 is 0. So, x is equal to 1 is a root and x is equal to 1 is also a root. That means x is equal to 1 is a repeated root of it. But whereas if you substitute in f of x, it will be 1 plus 2 plus 3, that is 6. 6 modulo 5 is 1. So, 1 is not a root of f of x. So, x is equal to 1 is a root of g of x, but 1 is not a root of f of x. You check. I have already explained. So, the answer to this question is option 1. So, that is the most easiest question that has appeared in the TS set exam 2023 in the October session. Agreed. Let's move to the next one. Right. So, here is a question. Here is a question which has appeared in 2000 TS set 2019 and 2023 March. And the question number is 71 in both the question papers, and the question IDs are different. You can see these are the question IDs, they are different. That means the same question with the same question number is given in 2 consecutive examinations. Anyway, so let f, the field, is equal to z by 2z. That is z2. That is z2 is integers modulo 2. Right. Number of elements in this fx by x square plus 1. It is the fx is the polynomial ring over f by bracket x square plus 1 means the ideal generated by x square plus 1 is, we are given 4 options. Right. So, let us now discuss. We have the given field. The field is f z by 2z, that is z2 consisting of 0, 1. And under addition modulo 2 and multiplication modulo 2, it is a field. Great. Now, f of x means the polynomial ring over the field f, that is z2x. That means the set of all polynomials with the coefficients coming from z2, and this forms a polynomial ring over z2. Now, let fx is equal to x square plus 1, and the bracket x square plus 1 will will be an ideal for f of x or z to x. So f of x, capital F of x by the ideal generated by f of x. That means z to x by the ideal generated by x square plus 1 will form a quotient ring. And what is the question? The question is the number of elements. So how the elements will look like in this z to x by the ideal generated by x square plus 1. It is the ideal I plus a plus bx, where ab belongs to z2. Like these are cosets. These are cosets. So the I means the ideal generated by x square plus 1, where ab takes values z2. So a takes 2 values, b takes 2 values. Right. When a takes 2 values, b takes 2 values, the number of elements in z to x by x square, the ideal generated by x square plus 1 will be 2 into 2, that is 4 elements will be there. The number of elements in the ring fx by the ideal generated by x square plus 1 is 4. Mind you, here this polynomial x square plus 1 is reducible over z2. Why? If you substitute x is equal to 1 plus 1, 2 modulo z2 is modulo 2 is 0. So it is reducible. It is not irreducible. Don't be under the impression that fx by the ideal generated by fx is a field. No, it is just a quotient ring. Agreed. So the answer to this question is option 4, where the 4 answer is there. So that is the detailed discussion of the solution of this problem, and it is also a very, very easy problem. Now, I will briefly talk about the definitions of irreducible polynomial and a reducible polynomial. So, to start with, we have D, an integral domain, right? And a polynomial fx belongs to D bracket x. D bracket x will be, or it's a polynomial ring over D, the set of all polynomials whose coefficients are coming from D, that forms a ring. So fx belongs to D of x. That is neither the zero polynomial, it is not a zero polynomial, nor a unit in dx. So who are the units in dx? The units in dx is all those elements which are invertible elements of D. That's all. So is not a unit in dx. F of x is not a unit in D of x. Is said to be irreducible over D. Irreducible over D if whenever f of x is expressed as the product f of x into g of x, f of x is equal to g of x multiplied by h of x, with g of x and h of x coming from D bracket x, then either g of x or h of x is a unit in D of x. That means whenever f of x is expressed as a product gx hx, where gx hx are elements of D of x, then g of x, h of x, then either g of x is a unit or h of x is a unit. Then it is said to be irreducible. Right. So now, and a non-zero, non-unit element of D of x, that means a polynomial which is a not zero, not a unit element of the polynomial ring D of x, that is not irreducible over D, is said to be reducible over D. Reducible over D. So that means whenever f of x, that means f of x can be written as a product of two polynomials of lower degree than that of the degree of f of x, or neither g of x nor h of x is a unit in D of x. Any one of the properties you can take. Now, let us take a very simple example. Let f of x is equal to 2x plus 2 belonging to the polynomial ring R over x, where R is the field of real numbers. Now, you see f of x is written as 2 times x plus 1, where 2 is a unit in R of x. 2 is invertible, no, in R. So, therefore, 2 is a unit in R of x. So it is written as a product of gx hx, where either g of x or h of x is a unit. So it is an irreducible. It is an irreducible polynomial in R of x. Agreed. Now note that f of x is equal to 2 times x plus 1 is reducible in z of x. Why is reducible in z of x, where it is written as the product of two polynomials whose degree is less than, so 2 into x plus 1 is reducible in z of x, since neither 2 nor x plus 1 is a unit in z of x. Why 2 is not a unit? Because you are talking about in z. In z, 2 is not invertible. 2 is not invertible. So it is reducible. It is not irreducible. Therefore, it is reducible. So be careful about these definitions. And irreducibility depends on D, that integral domain D. So in R of x, it is irreducible. In z of x, the same polynomial is reducible. So be careful about it. And there is a test that is coming. Now, the reducibility test for degree 2 and 3. That means the polynomials of degree 2 and 3, there is a reducibility test. Very easy test is there. But it depends on the degrees, degree 2 and 3. Let f be a field. If f of x belongs to the polynomial ring capital F bracket x, right, and degree of fx is 2 or 3, then f of x is reducible over f if and only if fx has a 0 in f. This test is applicable only for polynomials of degree 2 or 3. Fx is reducible over f if and only if fx has a 0 in f. That means take the polynomial f of x. See the zeros of f of x in f. So that means f of x has zeros in f for degree of the polynomial 2 or 3, then it is reducible. That means it is sufficient to look for the zeros of fx in f. If they are there, then it is reducible. Right. Note, the polynomials of degree larger than 3, that means greater than 3, that means for polynomials of degree greater than or equal to 4, may be reducible over the field f, and when you look for f, they will may be reducible over a field, even though they do not have zeros in the field. So you take f of x, whose degree is, let us say, 4, and look for their roots. They do not, that means this polynomial have no roots, no zeros in that field f. So then it doesn't mean that it is irreducible. Then it is reducible. But still it may be reducible. That means this test doesn't hold for polynomials of degree greater than or equal to 4. So let's give an example. In Q of x, the polynomial x to the power of 4 plus 2x square plus 1 is a polynomial. Now if you look for the roots of this polynomial in Q, we do not find any roots, because it is coming out to be complex roots. But whereas it is reducible, so it doesn't mean the roots are not there in Q, doesn't mean that this polynomial is irreducible. It is reducible. Why? Because this is written as x square plus 1 whole square. That means it is written as the product x square plus 1 multiplied by x square plus 1, g of x, h of x, where both are having the polynomials of degree less than f of x. But this polynomial has no zeros in Q. So it is reducible. It is reducible. So the results. We have a famous theorem. Let f be a field and p of x be a polynomial from the polynomial ring f of x. Then the ideal generated by p of x is a maximal ideal in f of x if and only if p of x is irreducible over f. So if p of x, the ideal generated by the polynomial p of x is maximal ideal if and only if p of x is irreducible over f. Great. We have a beautiful corollary for the quotient ring f of x, f bracket x by the ideal generated by p of x. In the above case, it is a field. So let f be a field and p of x be in a irreducible polynomial over f. Then fx by the ideal generated by p of x is a field. Right. F is a field. F must be a field. Fx is the polynomial ring. Px is an irreducible polynomial. Then fx by the ideal generated by p of x is a field, and it is if and only if. It should be irreducible polynomial. Right. If f of x belongs to zpx, where the zp is a finite field of order p, where p is a prime number. So f of x belongs to zpx, is irreducible over zp, where p is a prime, and the degree of fx is equal to n. Then zpx by the ideal generated by f of x is a field from the above, because it is irreducible. The number of elements also you can say in this field. The number of elements are p to the power of n. So zpx by the ideal generated by f of x is a field with p power n elements. Let's have an example. A good example. You have to find the number of elements in the ring Z2x by the ideal generated by the polynomial x cube plus x plus 1 is. We are given 4 options. Agreed. We have the field Z2, addition modulo 2, multiplication modulo 2, where Z2 is 0, 1. These are the residual classes modulo 2. Agreed. Let f of x is equal to the given polynomial x cube plus x plus 1. It is a polynomial of degree 3. Now, f of 0, substitute 0 plus 0 plus 1, 1, not equal to 0. F of 1, 1 plus 1 plus 1, it is 1, not equal to 0. So, this will tell you f of x is irreducible over Z2. Agreed. It is irreducible over Z2. Then you have this result. Fx belongs to zpx is irreducible over zp, where p is a prime number and a degree of fx is equal to n. Then this zpx by the ideal generated by fx is a field with p power elements. So z2x by the ideal generated by x cube plus x plus 1 is a field with p power n elements. P is 2. The degree of the polynomial is 3. So 2 cube, that is equal to 8 elements. So the number of elements in the ring it is given is okay, ring, but it is actually a field, and you have 2 cube, that is equal to 8 elements. The answer is option 3, where 8 is appearing. So let's now move to a question that has come in TS set 2023 in the October session. So the question number is 80, bearing this question ID. The question is, a field among the following is, we are having options. 4 options are given. Agreed. Now, first option, let us take. So we are given the polynomial ring C of x, where C is the field of complex numbers, and the polynomial fx is x square plus 2. So that is the option 1. Right. Now, note that x square plus 2, when you is equal to 0, solve for it. X is equal to plus or minus I under the square root of 2 belongs to C or the roots of fx. And is a degree 2. Is a degree 2. Then we are looking for the roots of fx. So the roots are there in C. Therefore, fx is not irreducible over C. It is a degree 2. Therefore, it is sufficient if you look for the roots. Right. Is not irreducible. So therefore, Cx by the ideal general by fx is the C of x, C bracket x by the ideal general by x square plus 2 is not a field because it is not irreducible. When it is irreducible, then the f of x by the ideal general by p of x, when p of x is irreducible, then it becomes a field. It is not. Agreed. Go to the option 2. Let f of x is equal to x to the power of 4 plus 4, and you have to look for in q of x, where q is the field of rational numbers. Note that f of x is equal to, you can write this as, see, normally people look for the roots of x to the power of 4 plus 4 in q. We don't have the roots in q. So it doesn't mean then it is irreducible. I told you, for polynomials of degree greater than or equal to 4, so that looking for the roots in the field doesn't work. So you have to go for the definition. F of x is equal to x to the power of 4 plus 2. Then it is written as x square plus 2 whole square minus 2x whole square. It is adjusted. So you apply a square minus b square, that is a plus b into a minus b. You get these two factors. So that means f of x is written as g of x multiplied by h of x, where the degrees of the polynomial gx and hx is strictly less than the degree of f of x. Therefore, it is reducible. It is not irreducible. It is reducible. So therefore, you can also talk about these two. Neither this nor that is a unit in q of x. Okay, this is also all right. So this implies f of x is not irreducible over q. It is reducible. You are able to factorize, right, to proper factors. So fx is not irreducible. Therefore, q of x by the ideal generated by x to the power of 4 plus 4 is not a field. Right. So now let's look at the option 3. So we have already seen option 1 and 2 are not fields. Let's go for the option 3. So you have f of x and the polynomial ring is Z5 bracket x. Z5 is the finite field with 5 elements. Right. F of x is equal to x square plus 3x plus 4. So it is of degree 2. Let's look for the roots in Z5. Now f of 0 is equal to 4, not equal to 0. F of 1 is 1 plus 3 plus 4, 8 modulo 5 is 3, not equal to 0. F of 2 is 2 square plus 2 plus 4 modulo 5 is 4, not equal to 0. F of 3 is equal to 2, not equal to 0. F of 4 is equal to 2, not equal to 0. So therefore, f of x is irreducible over Z5. It is of degree 2 and in finite field. So when it is irreducible, Z5 bracket x by the ideal generated by f of x, that is Z5 bracket x by the ideal generated by x square plus 3x plus 4 is a field. And by the way, how many elements it will have? It will have p power n. P is 5. N is the degree of the polynomial is 2. It will have 5 square, that is 25 elements will be there in this field. But we are given which one of the following is a field, therefore it's a field. Look at the fourth one. So Z5x, the polynomial ring, and f of x is x square plus 2x plus 2. Now f of 1, if you substitute, if you f of 1 plus 2 plus 2, that is 5 modulo 5 is 0. So f of x is not irreducible over Z5. So it is reducible. You are able to find a factor x minus 1. Anyway, so z5x by the ideal generated by f of x, that is z5x, the ideal generated by x square plus 3x plus 4 is not a field. Therefore, which one of the following is a field? The option 3. So therefore, the answer to this question is option 3. And that is the detailed discussion of the problems on rings that have appeared in the TS set examinations with relevant definitions and the rules, the theorems that I have applied, I have discussed in detail. Right. I am sure that you have understood the solutions of the problems, the concepts that I have discussed, and the theorems that I have explained in this video. I have been making videos for the benefit of IIT JEE Mains students and for the benefit of the CSIR NET students and for the benefit of TS set, AP set, JAM, GATE aspirants also. If you like my videos, please like, share and subscribe. Thank you. I wish you all the best and thank you.